please join me in welcoming to the Distinctive Voices podium, Dr. Rose Yu.
Hi, good evening. Thank you so much for spending the time and listen to what I'm going to share with you. So I direct the Spatial Temporal Machine Learning Lab, and here is a logo in my lab. You can see there is a rose in the middle of the logo, and what's not obvious is that there is also a letter of space and time, S and T, hidden in this logo. And our mission is to accelerate scientific discovery through AI by developing algorithms and models that can make sense of space and time. So there's a lot of hype and excitement around AI, particularly in science. AI had made huge success in scientific field. Last year, there were 2 Nobel Prizes awarded to AI-related researchers. One in physics, basically awarded to John Hoffield and Jeff Hinton for their fundamental contributions in artificial neural networks or deep learning. And the other award of Nobel Prize in chemistry was awarded to a group of researchers working on AI for protein design and structure prediction. So I would say the Nobel Prize in physics is more about science for AI, using scientific principles to design AI algorithms, and the Nobel Prize in chemistry is more about AI for science, that is to develop AI tools to accelerate scientific discovery. So with a lot of excitement, people start to think that AI is actually learning the physics of our world, in particular a group of researchers at OpenAI. So last year, they released this software called Sora. They claim that Sora has learned the real-world physics such that when you type it a particular text prompt, it will generate realistic videos for you. So let me give you this example. If I ask Sora to generate a sports telecast scene of a gymnastic performing an aerial flip during a floor routine. So if a model really understands physics very well, then it should be able to generate realistic videos. So this is what Sora generates. And clearly, it hasn't really learned the physics. And we are very far away from AI to learn the real physical world. And it may be entertaining for you by looking at this video, but for solving real-world science and engineering tasks, making mistakes like this can be consequential. So my research focused on injecting physical knowledge into AI models. Because in AI, we are very proud that we can have very expressive models, and the algorithms are very computationally efficient. The models can generalize to unseen scenarios. However, current AI still lacks a framework of physical reasoning. They are mostly black box models and are very difficult to interpret. They also suffer from high sample complexity, meaning that we often require millions, if not billions, of data points to train. And in a lot of scientific experiments, even collecting a single data point can be very expensive. So in AI, perhaps one of the most well-known tools is neural network or deep learning. And then there's other tools such as graphical models or probabilistic inference that we often use. On the other hand, physics as a fundamental tool in the scientific field brings rich domain knowledge. They develop models from first principles, so they're rather easy to understand and interpret. These models can also have very low sample complexity. You often derive them with only a couple data points. But physics models rely on very rigid assumptions of underlying phenomena. They're extremely expensive to compute for complex phenomena. And then for each system, we have to derive a different model, so they don't really generalize to new phenomena. In physics, we have a lot of concepts such as differential equations or the principles of symmetry. As you can see, AI and physics have almost complementary strengths. What if we can bring the best of two worlds together, using the domain knowledge from physical science to inform the development of AI, and then enable AI to give a much more expressive and efficient tool to solve tasks in physical science? And the fundamental goal of this hybrid system is to enable our AI to be more trustworthy by baking in first principles and domain knowledge in this field. So I wrote a survey article with my student published at PNAS last year to give an overview of this field, in particularly focus on learning dynamical systems from data. And that is what I'm going to talk about in today's talk. So in this paper, I categorized this area called physics-guided deep learning. So deep learning is the driving force of the modern AI, and it's powering a lot of this recent development in large language models, diffusion models, etc. So in the survey paper, I categorized different ways to inject physics into the design of deep learning models. From very strong physical inductive bias, we can use residual modeling. And then if we have slightly weaker inductive bias, we can develop trainable operators. And at more higher level, if we only have some vague inductive biases about symmetry, we can use equivariant learning. And if we almost know nothing about the underlying physics, then we can take this idea of this entangled representation. So in today's talk, I will give examples for the first three types of methods: residual modeling, trainable operator, and equivariant learning. If you want to know more details about this framework, I encourage you to take a look at our survey paper. So AI and science really plays this integrated role throughout different steps of scientific discovery, starting from collecting observations to generating hypothetical questions to test out the hypothesis using experiments and analyzing the data collected from the experiment and then draw a conclusion to lead to a new set of hypotheses. This kind of feedback loop can be accelerated by AI in almost every step. And I will show you how we can use physics-guided AI to accelerate different steps in this scientific discovery pipeline. So let's start with residual modeling. So in this case, if we want to learn a model that maps from some input to output, and we happen to know there is a really good physics model, and we can represent it as the function g, but the physics model can be overly rigid, and they make relaxed assumptions about complex world. So obviously, the physics model can be biased. In this case, we can just use the deep learning model to correct the bias of physics-based model such that it can better map the complexity of real-world data. And that's a very simple idea of residual modeling. But this idea alone gets us the first place in forecasting COVID-19 incident cases with 40 national teams in the United States. In these tasks, there are historical data about number of death cases reported by CDC, and the goal is to forecast the next 4 weeks incident deaths with confidence intervals. And our team was ranked #1 among 40 national teams in this competition solely based on this idea of residual modeling. So our physics-based model was one of the leading models in physical modeling for epidemiology developed by our collaborators. GLEAN stands for Global Epidemic and Mobility Project. It combines real-world data on populations and human mobility with very elaborate stochastic models of disease transmission. However, these models are computationally inefficient, and they often ignore the delay in the reporting as well as some latent variables, such as those people who are infected but do not show any symptoms. Because of this bias in physics-based models, we train a hybrid model called deep GLEAN. Deep stands for deep learning. In this case, we take the simulation data from GLEAN, subtract that with the observational data reported by Johns Hopkins Applied Physics Lab. In this case, we can understand what is the bias from the physics-based model. Then we use a deep neural network, in this case, a sequence-to-sequence model that was developed originally for machine translation, that we can map the sequence of time series from the past into the sequence of time series into the future. So this is the performance of our deep GLEAN model compared to purely deep learning model as well as purely physics-based model GLEAN. And this is showing the forecasting mean absolute error over the next 3 weeks. So if you look at the green bar, which is a pure deep learning model, the performance is actually very bad because in COVID-19 modeling, we had very sparse data points, and there's a lot of missing values in the data due to reporting delay. So using a pure data-driven approach like deep learning basically couldn't learn any signal from the data. But using physics-based model alone is still insufficient because of the biases in the physics modeling. So by combining these two models together, we have the best two worlds. And then we also added the confidence level to our hybrid model using uncertainty quantification techniques. And this is showing the forecasting performance of different models. The black line is the ground truth, which is the observational data. And then the red one is our hybrid model, deep GLEAN. You can see that deep GLEAN, the red line, correctly anticipates the changes in the trend of COVID incidences, and then therefore lead to more accurate forecast into the future. Another important challenge in epidemic modeling is to generate what-if scenarios. Policymakers often want to understand the impact of different policy, such as school lockdown or the vaccine allocation. But to understand what-if scenarios, they need to run these very complex stochastic simulations. So in epidemic modeling, the question is, can we accelerate this process such that our policymakers can really make real-time decisions? Just to give you a sense of how expensive to generate one scenario, because we're modeling at global level and we discretize the globe into 200,000 subpopulations, to generate one scenario takes about 6 to 9 hours. And we often have to simulate several hundred, if not thousands of scenarios. And it's definitely not enough for real-time decision-making, for scenario creation. The goal of deep surrogate modeling is to develop a deep learning model that can emulate the behavior of complex stochastic simulations, but much faster. So in order to train this model, the common way would just be simulate a lot of potential scenarios using physics-based simulation, and then use these simulation data as training data. However, this process requires us to scan through all different combinations of parameters in physics-based simulation. So for this particular simulator, it has about 120,000 parameters, and most of them are continuous. So if we want to scan through all the combinations of different parameters, then we will never have enough training data to train our model. So instead, we have a simulator in the loop type of learning scheme. The idea is that we will train a deep learning model initially with only a very small amount of simulation. And then by using the surrogate model, we can estimate the uncertainty of the model at different parameter regimes. So then we can evaluate the confidence level of a surrogate model at different parameter regime and select the parameter settings that the model is most uncertain about. And this means the AI model right now needs more information to improve its confidence. So then we will query the simulator to generate more training data and add this training data into the deep learning model to further improve this model. And this pipeline, using uncertainty as a guidance to iteratively sample the data from simulator, is called Bayesian active learning. And through this development, we also proposed a new type of criteria to select the simulation called latent information gain. Because in the previous literature, people often use information gain to select the samples from simulation, which means we want to select the data set that gives us the maximum amount of information. However, this kind of information gain criteria need to be computed in the parameter space, which in our case is 120,000. So instead of computing the information gain in the observations, we're computing the information gain in a much lower dimensional space, the latent space. And we call it the latent information gain. And using Bayesian active learning with latent information gain, we can save 68% of the training data required to train the surrogate model. And that also translates to significant speed up in generating this deep surrogate model. So this is a recent collaboration with CDC as part of the InsightNet collaborative partner network. We developed a Gleam AI, and the left one, Gleam, is the physics-based model. The right one, Gleam AI, is our hybrid deep surrogate model. As you can see that the samples from these two models are almost exactly the same, but to run Gleam for 100 simulations, it takes about 3 hours. But to run ours, it takes about 50 seconds. And you can also look at the distributions of these models, and you can see the distributions from our model almost perfectly match the physics-based simulator. So CDC right now is testing our tool for future control and management of seasonal flu, and hopefully our model can really accelerate the policy making in epidemic control and prevention. So the next paradigm is called trainable operator. In this case, we don't actually have a very good simulator from physics, but we have some good understanding of the underlying operation in the physical field. For example, if we have a good understanding that underlying dynamics governed by Laplacian equation, then we can replace the original Laplacian operator in this equation with a trainable deep learning model. So the benefit of trainable operator is that the learned operator still follows the same mathematical characteristics as existing operator, but then make it significantly more flexible because we don't need to manually specify the Laplacian operators anymore. Instead, we're learning how to operate on the functional space. To give you an example, we worked with experts in turbulence to speed up the simulation of this type of complex fluids. And what you're seeing is called the Rayleigh-Bernard convection. It occurs when cold fluid on the top interacts with the warm fluid in the bottom, and it creates very intricate turbulence patterns. To show this couple seconds video, it actually takes several months to simulate. And our goal is to develop deep learning surrogate models that can emulate turbulence dynamics, but much faster. We developed turbulent flowlet. The idea was really inspired by techniques in computational fluid dynamics modeling. In particular, this algorithm called Reynolds averaging large eddy simulation. And essentially, given the velocity field W over space c and time t, the Ren's LES coupling will first use a spatial filter to average out the spatial velocity field. Afterwards, it applies a temporal filter to filter out the temporal variations in the fluid flow. Traditionally, in CFD, spatial filter and temporal filter are both hand-designed. So in order to relax this assumption in existing CFD algorithm, we proposed to simply replace these manually designed filters with trainable deep neural networks. And the RANS-LES coupling also represents the multi-scale decomposition of turbulent flow. So on the right plot, what you're seeing is the variation of kinetic energy over the wave number, and large waves or large eddies have a small wave number, and the small waves have large wave number. So this is our model. As you can see here, given the velocity field of the turbulence, W, we pass it through a spatial filter, then a temporal filter. For each component or each scale of the turbulence, we use another neural network to predict its future. And afterwards, we use a shared decoder to capture the interactions across field. For both the spatial and temporal filter, they're nothing but convolutional neural network, so they are completely learned from data. We can look at the prediction performance of our model. We compared our model, TFNet, with many state-of-the-art models for turbulent emulation, and our model is faster than lattice-Boltzmann method. That was a numerical method used to generate the training data. But most importantly, when we compare our model with existing video prediction models that was not physics-guided, we can see that our model really learned the correct physics compared to other data-driven models. What you're seeing is, on the right plot, is the energy spectrum over the wave number, and this diagram is known as the Kolmogorov scale plot. So there is a black line, which is the ground truth. That's what we want to match. And then the two variations of our model in blue and yellow closely follow the trend in target, whereas other UNet and ResNet, that was the state-of-art models for video prediction, completely failed for large wave number regime, which corresponds to this high-frequency phenomenon in turbulence. So if you look at the actual videos from the prediction, the target is this rotating turbulence in 2 dimensions, and then our model can accurately capture this rotating pattern while also maintain intricate small-scale dynamics. In contrast, ResNet and GANS, which were state-of-art video forecasting model, they could not capture the small-scale dynamics, even though they do capture the large-scale rotating pattern in this turbulence. We further extended the work to capture the fluid dynamics of the climate, because the example I showed you for Rayleigh-Bénard convection actually was the inspiration for a lot of the work we do in climate, because the cold fluid and the warm fluid interaction is an example of the famous phenomenon in climate called El Nino, where the cold fluid in North America interact with the warm fluid coming from South Africa, and that creates extreme weather that we cannot anticipate. So fluid dynamics is fundamental to many climate phenomena, from the hurricane to the wildfire to the ocean turbulence and many more. So in order to understand this phenomenon, we need better models. Traditionally in climate, the scientists would rely on complex numerical simulations based on coupled PDEs to simulate future evolution of the climate. And this type of simulation often takes months, if not years, to generate. So we developed our surrogate model based on this idea of diffusion model. And diffusion, obviously, is also a known operator in mathematics. So the idea of diffusion model is really takes the concept of diffusion operator in stochastic processes, where it aggregates an image gradually like a stochastic process. It turns an image of the data into white noise, but most importantly, it learns to reverse this process, and then the noise then can be transformed into the data. So the standard diffusion have this forward and reverse process, where the forward process perturbs the data into noise, and then the reverse process generates data from noise. the idea of a trainable operator in this research is to learn the diffusion process that can generate the data distribution. However, most of the diffusion models so far were only designed for static images, not for physical dynamics. We proposed a completely new type of paradigm for diffusion model based on dynamics-infused diffusion, also known as the diffusion framework. So if you remember what I talked about, for a regular diffusion model, we will gradually add Gaussian noise into the data and then reverse engineer that to generate data from noise. And this process completely ignored the underlying physics in the data. So what we proposed is instead we try to learn the underlying physics, which is the diffusion operator from data. Instead of adding Gaussian noise to each step to the data, we will learn the degradation process using another neural network, which we call the temporal interpolation network. So in this way, we can save all the intermediate degradation steps and use that as intermediate forecasts. So that allows us to significantly speed up the sampling process of diffusion models. As a proof of concept, we tested this idea on Navier-Stokes equations. And then what you're seeing is the video evolution of fluids. The top one is the ground truth, and the middle one is the baseline, and diffusion is shown on the bottom. So what's different between diffusion and the TF-net model I showed before is that this model is probabilistic. So we can draw multiple samples from this emulator, then we can understand the confidence interval and assess the uncertainty of the prediction. So we also looked at the forecast on sea surface temperature and Navier-Stokes equations, and our model is able to emulate these complex dynamics, but much faster. We further extended this framework to emulate global climate. And as I mentioned before, climate models takes about 6 months to simulate at global scale. And using diffusion, we can have 25 times speed up. And here is a video showing the prediction from our model. The left one is coming from a physics-based model, and you can see the wind is changing globally, having very intricate turbulent patterns. And the middle and the right are two samples from our deep surrogate model. Because the model is probabilistic by nature, so we can generate multiple samples from this model. And you can see that model samples emulate the dynamics of physics-based model quite well. It also captures the variability very well. And this type of variability allows us to generate ensembles of climate projection, and that help us to understand the global trend of climate. So compared to the existing deep learning-based baselines developed by Allen Tull Institute, ours achieved 70% improvement in terms of forecasting accuracy as well as uncertainty quantification metrics. And this work also won the Best Paper Award at one of the top machine learning conferences. Finally, I wanted to talk about this framework of equivariant learning. In this case, we don't have a good physics-based simulator. We also don't know what is the underlying mathematical operators used for modeling the physical dynamics. However, we have some very vague ideas about the physics in the form of symmetry, because symmetry is a very fundamental concept in physical science. Again, if we want to learn a model that maps from input to output, we want to constrain the model to satisfy this equality, which means if I apply a group transformation to the input, then this transformation automatically applies to the output, then I can say this mapping or this function has a particular symmetry. The simplest example you can think of, if we have a ball, and when I rotate the ball, you can still recognize the ball, which means our cognitive system have built-in symmetry that help us understand the object and the physics around our world. So mathematically, to describe the symmetry, we need to think about the concept group. So a group is a set with a composition mapped to itself. An identity is an element of the set, and for every element, there is an inverse element. For example, if we think about 2D rotation as a group element, which corresponds to special orthogonal group in 2D, of course, if we don't rotate this object, that means it's an identity element. And if we rotate this object clockwise 60 degrees, and obviously we can also rotate this object counterclockwise 60 degrees. These two types of operations corresponding to the group element and its inverse. So once we have this concept of group, which essentially is a transformation, then we can define what we mean by symmetry. So if a function does not change when we transform its input, then we say this function is group invariant. So it does not change when we transform its input. More generally, if we transform its input, this transformation also applies to its output, then we say this function is group equivariant. So equivariant is more general notion of invariant. And an example of equivariant is that if we're looking at the river flow, and then the start of the river flow rotate by a certain angle, then the downflow also will rotate correspondingly. And that means this river flow has rotation equivariance. We want to build neural networks that can satisfy this type of symmetry, because in that case, they will better model the underlying physics that we know. Another mathematical concept that we use is Lie group. So Lie group is a particular type of group that is continuous. So you can look at this green ball, and this entire smooth manifold is a Lie group. So for every element, there is a Lie algebra, which corresponds to a vector space at a particular position of this manifold, and that's shown in this pink rectangle. That's the Lie algebra. So Lie algebra helps us to move any point on the Lie group to any other point on this manifold. And using this concept, we can build neural networks that can do amazing things in symmetry. So I wanted to discuss our framework to automatically discover symmetry from data. And our work was inspired by this model in deep learning called generative adversarial network, or GANs. So what you're seeing is a lot of images of human faces. And these faces do not exist in the real world. There's actually a website called These People Do Not Exist, because the faces are completely generated by AI models. But they're quite realistic, and the way you can achieve that is through a model called GANs, Generative Adversarial Network. What it does is that it tries to transform the random noise into a fake image, and then in order for the model to generate a realistic image, you need another model, which is called the discriminator, to judge whether generated image is real or fake. So this model trains two models, a generator and a discriminator. A generator is responsible for generating the data, in this case, a fake image, and the discriminator is responsible for judging the quality of the samples to tell the fake from real. And when the discriminator is actually successfully fooled, then we know the generator is successful. That means it has generated the image so real that the neural network cannot tell. So the discriminator and the generator play a two-player game, and this model is known as one of the best ideas in deep learning in the past 10 years, quoted by the Turing Award winner Yann LeCun. So our model draws inspiration from this architecture, but using the mathematical tools of Lie group, we call it Lie GAN. When we think about symmetry in the data, that means when we transform the data, we cannot tell the difference. So in this case, we also have a generator, but instead of generating fake data, we're generating group transformations. We parameterize the Lie generated algebra as a bunch of trainable weights, and then whenever we sample from the generator, we create a new group transformation. We also have a discriminator whose job is to discriminate between the real data and the fake data. The fake data is the data that has been transformed by this group element that we sampled from. If the data distribution has intrinsic symmetry, then the model will be able to discriminate, then the discriminator will not be able to discriminate the real data and the fake data because that's the intrinsic symmetry in the data distribution. So we also play a two-player game between the generator and the discriminator, but the discriminator's job is to tell whether the symmetry is actually real in the data. So through this architecture, we actually apply the model to the Large Hadron Collider data from high-energy particle physics. In this case, we have accelerators that accelerate the particles at the speed close to the speed of light. And when these particles collide with each other, they often generate new type of particles. The task is to understand whether there are different types of particles, trying to group them into different types. And this task is known as the jet tagging problem in high-energy particle physics. Also, in high-energy particle physics, Lorentz symmetry is a very well-known symmetry used by Albert Einstein for his general relativity theory. And using our model, Ligand, we can successfully discover the Lorentz symmetry from the data alone without really understanding the deep math behind particle physics. When we showed our results to our collaborators in physics, they were stunned. We also used the discovered symmetry to build neural networks that have baked-in symmetry. And eGNN is a model that does not have the Lorentz symmetry. Lorentz LED in gray is a model developed by expert physicists who put their domain knowledge into the design of deep network and obtained the model LorentzNet. And Ligand is a neural network that automatically discovered the Lorentz symmetry with almost no knowledge in physics, but it was able to match the prediction performance of LorentzNet that was the expert designed model for this task. Another challenge in discovering of scientific field is to understand the simpler structure in complex data. In this example, if we're looking at the complex turbulence of reaction diffusion system, the model should be able to recognize there's a much simpler representation that is a rotating particle shown on the right. So how can we design an AI model that can automatically figure out this much simpler and easier to understand structure from data? And that's what we used in this paper called learning in a latent space. In essence, instead of discovering symmetry in this very complex high-dimensional pixel space, we want a model to automatically identify lower dimensional structure and then discover symmetry in the latent space. So we extended our previous model, Ligand, to latent Ligand, or LaLigand. Essentially, we have the same kind of generator that generate group transformations, but instead, we will use an autoencoder to automatically learn the much lower dimensional latent space. Using the latent space, we can again borrow the discriminator idea to discriminate original data and the data after group transformation. When the discriminator cannot distinguish these two sets of data sets, then we know we have successfully identified a symmetry from data. But now, in the latent space. We can use this technique to enable automatic equation discovery, essentially trying to recreate what Newton has by observing the apple falling from the tree multiple times and coming up with the equation F equals ma. And here we want the deep learning model to observe the data multiple times and automatically come up with a governing equation without really knowing the deep math and physics in the domain. So we can use the symmetry as a guiding principle if we have the inductive bias of what the phenomenon we're looking for. If we have the symmetry built in, then the discovered equations are much simpler and symmetric. As you can see here, when we applied our method with a sparse regression technique to find governing equations, the equation that we discovered only have 2 terms. And then the 2D case, we can discover equations with perfectly symmetric parameters, which is desirable in a lot of the physical science. So science often prefers the principle of parsimony. By allowing models to imbue the principle of symmetry, we really can realize this principle of parsimony. So to conclude, computing and AI are really transforming our scientific discovery process. Science represents an exciting frontier for AI, and AI represents the most accelerating new instrument at the hands of scientists. So we can imagine a future where our scientists and AI agents work side by side from hypothesis generation to experimental design to collecting observations, analyzing the data, and generate a new set of hypotheses. AI will co-pilot with scientists at every stage of scientific discovery process, and scientists will provide the necessary guidance and physical principles to ensure our AI is conforming to the scientific truth and generating trustworthy predictions. With that, I want to thank you for the attention. You can reach me at my website with the email and phone numbers on my website, or follow me on social media. I would also like to thank the funding agencies for supporting this work. Thank you.